I'm Riana Rossouw. I manage the XRF and ICP-MS unit. Before we start, I would like to introduce the rest of my team. So in charge of XRF and mineral separation is Marley. In charge of solutions, ICP and CHNS is Shanae. And our mineral separation wizard is Herschel. Laser ablation ICP-MS is typically used on dry solid samples for in situ analysis of trace and sometimes major elements, often on samples that are difficult to extract for solution ICP. An advantage is that the sample is not diluted for any sample prep, so the technique has very low detection limits and also low levels of contamination. Analysis is mostly done on geochemical samples such as minerals or sediments, but also on biological material such as bone, teeth, or fish otoliths. Analysis is typically done at spot sizes from 10 to 100 micron, but continuous line scans at the same diameter can also be applied. Looking at geochemical applications, we do trace analysis on whole rock fusions after majors was measured by XRF. The silica, calcium, or aluminium content is used as internal standards to quantify the data. Samples are prepared by crushing the XRF fusions into chips. We mount up to 15 pieces from different samples into a 2.5 centimeter resin disc and then polish the sample surface. A mount map is created for each resin disc so that we can identify the samples once it is mounted in the laser sample holder. There are some limitations to the elements that can be measured. Lithium and boron are components of the flux, so they have to be excluded. Platinum and gold are often contaminants from the crucibles when fusing the samples, and volatile elements such as mercury, silver, arsenic, and selenium is usually lost during fusion. We also do in situ mineral traces, either in thin section or on grain mounts, where selected minerals are firstly separated, picked under a microscope, mounted in resin, and analyzed by SEM for major components and to identify specific features for analysis. So we have a mount with some apatite and zircon grains. We can have gold grains and gold shavings mounted into resin, or we can also do gold minerals included in thin section. Our instrument can also accommodate samples of random shapes and sizes as long as it has a polished surface. An example here is the measurement of trace element variations in thin layered calcites. In biological applications, the interest is often to investigate how changes in an environment was recorded by a species over a period of time. For instance, monitoring lead or mercury exposure by analyzing teeth or even hair, or if changes in the habitat is recorded in the growth rings of fish otoliths over their lifetime. For the otolith analysis, we rinse the sample in 1% nitric acid to remove any surface contaminants. Then we mounted it standing upright in the resin. Once the mount is set, it is polished down to the middle of the otolith, which is indicated by this blue line. The good polishing and imaging reveals growth rings in the otolith, and spots can then be made along the line indicated here in green, or even a continuous a line can be ablated to monitor differences over very high resolution. Another useful application is gridded ablations, where the data is combined to create coarse resolution compositional maps. So you have your sample grain, and the roster of points is continuously ablated over the sample surface. The data is then stitched together, and for individual elements, a compositional map can be created. Its advantage is the simultaneous collection of more than 30 trace elements over a short period of time, typically maybe even less than an hour, at a lower limit of detection than can be obtained with SEM analysis. The disadvantage is the lower resolution of this combined image maps than would be obtained from SEM or electron microprobe analysis. The sample format for the laser ICP analysis is dry solid samples, ideally with a flat polished surface. The sample must fit into either 2.5 centimeter round, thin section, or custom size sample holders, which then fit into our large format cell as part of our resolution instrument. The equipment in our laser ICP-MS lab includes 2 resolution 193 nanometer excimer lasers, which is interfaced either with a thermo element 2 sector field ICP-MS or an Agilent quadrupole or triple quad ICP-MS. The element is used exclusively for uranium-lead isotope ratio measurements because of its superior sensitivity, while the single quad is used for trace elements and the triple quad for both traces and selected isotope analysis. So let's have a look at the ablation process. The laser beam with a set diameter of about 30 to 100 microns is focused onto the sample surface for a period of time, where it volatilizes the sample material into a small dust cloud with various particle sizes from 0.5 to 50 microns. Helium gas flows through the cell and carries the sample material out, and then mix it with argon gas on its way to the ICP. The sample is then carried into the torch, where an argon plasma at about 6,500 Kelvin atomize and ionize the sample and all the elements contained in the sample material. The ionization efficiency of an element depends on its ionization potential. The ionization potential is the amount of energy required for that element to form an ion. The higher the ionization potential, the more difficult it is to ionize and the lower the sensitivity. Elements that ionize easily generates a lot of ions even at low abundance, so they will have very good sensitivity. If the element has an ionization potential higher than argon, it is not ionized in the argon plasma, for example, helium, fluoride, and neon. So what happens when a sample containing a number of elements is pushed into the high temperature argon plasma. All the elements in the sample is atomized and ionized simultaneously, some more effectively than others. Each element has one or more natural isotopes, all forming simultaneously during ionization, but at different abundance levels. When a sample with copper, for instance, is introduced, two different ions of copper is formed, copper 63 and copper 65. They've got the same chemical but different physical properties and different abundances. In the argon plasma, every single element in your sample has now been ionized from the analytes you are interested in, along with all the matrix elements. This soup of ions are then sucked through a set of metal cones with 1 mm followed by 0.4 mm opening. All the neutral species and light photons are rejected and do not continue further into the instrument. Complex processes within the argon plasma can cause some ions from either the sample matrix or the gas environment to recombine and form large new molecules with the same mass as an analyte to be measured. These are called polyatomic interferences. When identifying interferences, you have to consider the isotope masses of all the ions and see how they add up to know on what element mass they will interfere. For example, in sodium-rich samples, you can have sodium at mass 23 that can combine with argon at mass 40 to form an interferent at mass 63, which is one of the isotopes of copper. Another type is isobaric interferences, where elements have isotopes at the same mass. So titanium, vanadium and chromium all have isotopes at mass 50, but they each have another mass without any interferences. So titanium has an isotope at mass 49, vanadium at mass 51 and chromium at mass 52. So how do we minimize interferences? We can use collision cell technology to remove the interferences with helium gas, or we just choose isotopes free from interferences. For example, you can use copper 65 rather than copper 63 in high sodium samples. So in order to remove interferences, ICP-MS has a small cell filled with helium through which all the ions pass before it goes any further. The principle of interference removal is that in a small space pressurized with helium, the larger interference molecules, argon chloride in this example, are 99.9% guaranteed to all collide with the helium molecule, which will slow them down, while the small analyte ions, namely arsenic in this example, will collide less with helium and have a higher velocity. The cell barrier will then only allow ions at the specific velocity of the analytes to pass, while the slower interference are stopped. A specific voltage exists for all analytes of interest, so they are sequentially let out of the cell at the time the instrument wants to measure them. After the interfering molecules have been removed in the collision cell and the analytes exit, they pass through the quadrupole mass analyzer, where different voltages is applied that stabilizes only a single isotope mass at a time and pass it onto the detector. Therefore, it's a very fast sequential process with measurement for laser ablation typically at 10 milliseconds per isotope mass. Accuracy and precision of laser ablation ICP-MS is affected by a number of factors. Firstly, elemental fractionation. where the measured element composition, the element ratio or isotope ratio, is different from the true values due to ICP or laser parameters. Matrix effects also have a very strong influence. Different materials or similar materials with largely varying chemistry have different ablation properties, resulting in variation in mass load introduced into the ICP for measurement, causing either signal suppression or enhancement. Thirdly is the availability of matrix-matched reference materials. These are standards with similar physical and chemical properties to samples in order to correct for fractionation and matrix effects. So we will look at the ICP and laser ablation induced parameters separately, which will affect elemental fractionation during measurement. So firstly, the ICP-MS induced parameters that can lead to elemental fractionation is firstly the RF power. It should be high enough to volatilize particles of various sizes, thereby minimizing changes in plasma response due to sample loading. Secondly, interferences on analytes can cause incorrect results. One needs to have knowledge of plasma and matrix space interferences to select the correct isotopes or remove interferences. Thirdly, a shallow torch depth is best for optimal ionization of all elements and particle sizes in the sample. When we look at the laser-induced parameters that can lead to elemental fractionation, there are firstly those inherent to the instrument, namely the laser wavelength, where you can have either a 266, 213 or 193 nanometer laser. Secondly is the gas flows, which is also determined by the instrument configuration. Ideally you want to have helium only in the ablation cell for better heat transfer between laser and sample, and then a mixture with argon gas for transfer to the ICP, and also a small amount of nitrogen added to enhance sensitivity. Parameters controlled by the operator and dependent on the sample type is the fluence or the laser energy, the spot size, the frequency of the ablation or the pulse rate, and the ablation time. So let's look at how these parameters could result in element fractionation. When comparing ablations from two different lasers, you can see that the 266 nanometer laser produces badly shaped craters, here in images A and B, compared to the smooth craters of a 193 nanometer laser. These ablations are also in a helium-argon mixture, while the 266 nanometer ablations was only in an argon gas environment. The choice of laser and ablation gas is important to ensure that the ablated material has a uniform particle size distribution, ideally less than 100 micron, for easy ionization in the ICP plasma. The sample material determines the optimal fluence for uniform particle size and minimal melting of the sample. When looking at the ablation of high purity gold, a very low fluence resulted in a lot of melting, but little material was vaporized for transfer to the ICP, while 2.5 to 3 joules per square centimeter fluence proved to be more optimal. The ablation time should be set so that it is long enough to generate enough data points, ideally at least 20 seconds when measuring a lot of analytes. If it is too long, the laser crater gets very deep, like in this 35-second ablation, and the ablated material has difficulty being transported out of the crater. The sample matrix has a large effect on elemental fractionation. Different matrices ablate completely different, as can be seen for sulfide versus a zircon. So here you've got a lot of material being deposited on the outside of the crater, very little for the zircon material. The sample matrix has a large effect on elemental fractionation, as it determines the volume of material volatilized. For different matrices, different volumes of material is ablated at the same instrument settings. So just when looking at 22 karat gold and a NIST glass, if both samples contained 50 micrograms per gram of copper and a larger volume of gold material compared to NIST is transported to the ICP, it will give a larger signal than during NIST ablation, therefore a higher concentration is measured. In laser ablation ICP-MS, there are limited standards available that are a close match to the samples typically analyzed. The most widely used are the NIST glasses, doped with various levels of trace elements in a silica aluminium matrix. Several other artificial silicate glasses for a range of geological matrices are used as either quality control or main calibration standards. So in this mount we've got some NIST glasses as well as some basaltic glasses that we use as main and secondary standards. Rock powders with certified compositions are also available to make fusions and use as control standards for whole rock trace analysis. Few mineral standards are available and NIST is also used most often. Pressed powders, like in this mount, for carbonates and sulfides are available. They ablate different from solid material, but they have been found useful for carbonate material as well as bone analysis. Powdered plant reference materials can be pressed into pellets and used as standards as well. Any analytical sequence is set up in the standard sample standard format with typically 10 to 15 samples bracketed by calibration and control standards to correct for instrument drift over time. So this is our typical sequence. We have a number of different NIST standards in the beginning, some control standards followed by the unknown samples, and again some samples and control standards in between. For whole rock fusions, we do 2 spots of 100 microns on each sample, while for other applications the sample type will dictate the spot size, such as zonation patterns in zircons, which only allows 20 to 30 micron spot sizes. Every analysis consists of a 20-second gas blank, followed by ablation on the sample material, and then another few seconds of washout to remove ablated material from the sample line. The gas blank is then subtracted from the ablation signal to remove any background contamination from either a specific element, such as low amounts of mercury from the helium gas or within the ablation cell, or to remove interferences formed from the instrument gases. For instance, one of the isotopes of argon at mass 38 combines with the nitrogen gas introduced and can form a background interference on mass 52, which is chromium. In order to quantify the instrument response measured as counts per second for each element, a calibration curve can be constructed from analyzing standards, so analyzing a number of standards with a known concentration of each analyte and plotting it against the corresponding signal measurement. So for every standard analyzed at a specific concentration generates a specific number of counts, and it should plot in a linear regression line for all of the standards. So when you measure any unknown sample material and you generate, for instance, 1,000 counts per second, it can be related back to a specific concentration, maybe 80 ppts of uranium in this instance. Typically, you would like to see a stable signal for all of the elements for the duration of the ablation. So for every sample, you like to see this nice stable signal. However, this is not always the case. Sometimes you can have an ablation signal with several elements increasing at the same time or decreasing at the same time or independently, which is a clear indication that the sample material the laser is drilling into at a rate of about 3 microns per second is not homogeneous. The way ablation data is acquired in the form of a time-resolved signal is very useful to identify such features during an ablation, and will explain why repeat measurements could all produce different results, as you can see from these 4 different ablations on the same sample material. It is therefore very important to know the scale of homogeneity of your samples. So for the sample analysis shown in the previous slide, which was a gold, silver, copper alloy, the grain appeared completely homogeneous under the laser microscope. But when we imaged it by scanning electron microscopy, after seeing the 30 micron spot-to-spot variation in the chemistry, we found these copper-silver microtextures. As an explanation, when you look at the size and positions of spots 1 and 2, they do not represent homogeneous sampling of the material. So when you look at the silver distribution, spot 1 have a larger component of silver relative to spot 2. If you look at the copper at spot 1, it's got less copper in spot 1, more copper in spot 2. So a chemical composition could show you maybe 70% silver in spot 1, 25% copper, and a little bit of gold, while spot 2 could result in only 10% silver measured, 85% copper, and a little bit of gold. Spot 3, which is about 50 microns, is already an improvement, but as you can see, if spot 3 is moved over the area of spot 1 or spot 2, it will still not be completely the results will still not be completely the same, and you will still need at least 3 spots for an accurate representation of the sample chemistry. Please contact me, Riana Rossouw, for any specific analytical requirements. We are always keen to develop some new applications. Thank you for your attention.
For more information on Central Analytical Facilities, please visit the SAF website and like the Facebook page. For weekly info on our ICP XRF unit, please check out our LinkedIn page. We wish you all the best for your work ahead.